overall goal of this procedure is to measure the electrical characteristics of single crystals of single-layer thin-film materials with interesting electronic properties.
This method can help answer key questions in the nanoelectronics field, such as how single layers of different materials stacked on top of each other interact electronically, and what is the emergent electronic behavior of the resulting heterostructure. The main advantage of this technique is that it produces high-quality, defect-free multi-layer samples for transport measurement.
Though this method can provide insight into graphene, it can also be applied to other systems, such as transition metal dichalcogenides, topological insulators, and other layer materials.
Preparation of the substrate is covered in the text protocol. The flakes should be a high-quality bulk sample. To begin, exfoliate the sample flakes. Prepare 1 by 3 centimeter pieces of standard wafer dicing tape and expose a square centimeter of adhesive by peeling back the release paper. Press the adhesive portion against the bulk sample on the slide. Make sure most of the adhesive area is covered with the sample. Then, press the tape against the adhesive side of another piece and peel them apart. Continue doing this until the sample flakes attached to the dicing tape appear transparent. Then, press the tape with the sample flakes against a piece of prepared substrate. Peel the tape away, leaving the flakes adhered to the substrate. Inspect the substrate under a microscope. Note the position of a suitable flake on the substrate using the positional marks patterned onto the substrate. Proceed by using an atomic force microscope to measure the flake thickness. It should be less than 100 nanometers thick. Optionally, deposit sputtered silicon dioxide on the sample to create an insulating matrix and to hold the sample to the substrate. To produce heterostructures composed of multiple flakes, prepare stacks of flakes. First, make a transparent PDMS and PPC mechanical stamp as described in the text protocol. Next, using a micropositioner, position the stamp over the first flake of layered material in the heterostructure stack. Then, adjust the Z-axis to press the stamp down on the sample flake.
This step requires patience, precision, and careful attention to minor changes in the color of the PPC PDMS as it comes into contact with the sample flakes.
Next, heat the sample to approximately 40 degrees Celsius using a resistance heater under the sample. This increases the attraction between the PPC and the sample. After heating for 2 minutes, slowly lift the stamp. The sample flake should be attached to the PPC. Now, position the mechanical stamp with the attached sample flake over the next flake of layered material to be used in the stack. Watch the alignment carefully and slowly lower the stamp until the attached flake comes into contact with the next flake. Then, lightly press the sample. Next, heat the sample to 40 degrees Celsius for 2 minutes again. Then, slowly lift the stamp up, and the next sample flake should be attached, forming a stack. Repeat this process until a stack of the desired size is completed. Now, transfer the heterostructure stack to a new substrate by first gently pressing the stamp onto the new substrate piece. Then, heat the stamp and substrate to 100 degrees Celsius for 5 minutes. While still at 100 degrees Celsius, slowly lift the stamp, leaving the stack on the substrate. The first step of this protocol involves using images of the sample at 20x and 100x magnification to prepare a design for the electron beam lithography. The result is a 6-terminal Hall bar design. The next step is to pattern the design in PMMA. First, spin a layer of PMMA with a molecular weight of 950,000 onto a 4-inch wafer at 5,000 RPM for 2 minutes. Then, bake the wafer at 180 degrees Celsius for 2 minutes and let it cool for a few more minutes before using it. Now, load the sample onto the electron beam lithography system and, following standard protocols, print the pattern onto the PMMA-coated wafer. Then, etch the sample into a Hall bar mesa. Use a reactive ion etching system to etch the sample into a Hall bar using the mask patterned earlier. Once etching is complete, remove the PMMA with acetone, then rinse with isopropanol followed by water. To prepare the e-beam resist mask for the deposition of metal contacts, use 2 coats of PMMA. Make the first coat using PMMA with a molecular weight of 495,000 and the second coat with a molecular weight of 950,000. Then, use the electron beam lithography system as before to make a contact pattern on the wafer. The final steps are to deposit chromium gold metal onto the sample using an electron beam evaporator, followed by a metal liftoff. These processes are described in detail in the text protocol. For the magnetotransport experiment, first prepare an electrical transport package with fabricated sample. Next, firmly attach the package to the probe tip. Then, connect all the diagnostic devices to the probe. Secure connections to the temperature control channel and to the electrical measurement channels. Now, vent the airlock and insert the probe tip and lock it into place using a clamp and an O-ring. Next, set the transport measurements according to the specific probe type. Then, pump out the air and water vapor in the airlock for as long as needed using a vacuum pump. Close the exchange and close the airlock valves. Now, open the valve separating the airlock space from the measurement space. The next step is to introduce the required volume of gas into the probe space. Now, adjust the mini-Zorb and main Zorb temperatures as needed, and slowly lower the probe into the center of the measurement space. Then, send the system to near 0 Kelvin according to the probe type. Once the temperature has dropped, start taking transport measurements at a range of temperatures, magnetic fields, gate voltages, and so forth. A Hall bar device was patterned in graphene stacked on hexagonal boron nitride for a low-temperature magnetotransport experiment as described. This schematic shows the Landauer-Buedeker edge states that arise from the Landau levels. These edge states provide a transport mechanism to calculate the values of measured Hall resistances. The experimental parameters included exposing the device to magnetic fields as high as 12 Tesla, temperatures as low as 0.3 Kelvin, and gate voltages as high as 30 volts. The plateaus of the measured Hall resistance correspond to Landau level filling. This is a model example of the quantum Hall effect. At 6 Tesla, Hall resistance and longitudinal resistance were examined as functions of back gate voltage to describe the quantum Hall effect on graphene.
After watching this video, you should have a good understanding of how to produce high-quality, defect-free multi-layer samples for transport measurement via sample exfoliation, flake stacking using a micropositioner and microscope, and advanced nanofabrication tools.
While attempting this procedure, it's important to remember to be patient and precise. After its development, these techniques paved way for researchers in the field of nanoelectronics to explore novel quantum behaviors in graphene and graphene-boron nitride heterostructures.